All right, let's go. The search for life beyond Earth has operated under a specific assumption for decades, and that assumption is now being fundamentally revised. Here are 10 discoveries and developments in habitable exomoon science that suggest life is not rare, not isolated, and not confined to the places we originally expected to find it. Number 10, tidal heating changes the entire energy equation for habitability. The classical model of habitability depends almost entirely on one variable, which is distance from a host star. Too close and surface water boils off. Too far and everything freezes. This creates what is referred to as the habitable zone, a narrow orbital band where liquid water can theoretically persist. The problem with this model is that it only accounts for one energy source, stellar radiation. Tidal heating introduces a second energy source that operates on completely different principles. When a moon orbits a massive planet, gravitational forces deform the moon's interior in a cyclical pattern. That continuous deformation generates friction, and that friction generates heat. The amount of heat produced depends on the moon's orbital eccentricity, its distance from the host planet, and its internal composition. What this means in practice is that a moon orbiting a gas giant far outside the traditional habitable zone can maintain liquid water beneath its surface or even on its surface if atmospheric conditions allow. Jupiter's moon. Europa is the local proof of concept. It sits well beyond the snow line of our solar system, receives minimal solar energy, and yet maintains a global subsurface ocean estimated at twice the volume of all Earth's oceans combined. That ocean exists because of tidal heating. The discovery that this mechanism functions reliably in our own system means it almost certainly functions in others. Every gas giant with a large moon in a slightly eccentric orbit becomes a potential host for liquid water environments, regardless of how far that planet sits from its star. This single mechanism multiplies the number of potentially habitable locations in any given stellar system by an order of magnitude. Number 9. Magnetic field borrowing solves the radiation problem that was previously considered fatal. One of the primary objections to moon-based habitability has always been radiation exposure. A moon orbiting a gas giant, particularly a Jupiter-class planet, would be subjected to intense radiation belts generated by the planet's magnetosphere. This is a valid concern. Jupiter's radiation environment near Io and Europa is severe enough to destroy unshielded electronics within hours. But the relationship between a planet's magnetosphere and its moons is not uniformly destructive. The magnetosphere is a structured field with defined geometry. Moons that orbit at sufficient distance from the planet can sit within the outer magnetosphere, where radiation flux is substantially lower, while still receiving protection from solar wind and cosmic radiation that would otherwise strip the moon's atmosphere over geological timescales. This is the critical distinction. A moon without its own strong magnetic field, orbiting in open space, loses its atmosphere to stellar wind erosion over hundreds of millions of years. The same moon, parked inside the magnetospheric envelope of a gas giant, retains that atmosphere because the planet's field deflects the charged particles that would otherwise ablate it. Recent modeling work on exomoon candidates around gas giants in the habitable zones of K-type and M-type stars has demonstrated that this shielding effect is not marginal. It is the difference between an atmosphere that persists for billions of years and one that is gone in less than 500 million. Atmosphere retention is not a minor detail. It is the prerequisite for every other habitability factor, including temperature regulation, pressure maintenance, and ultraviolet filtering. A moon that can borrow its planet's magnetic infrastructure effectively bypasses one of the hardest problems in planetary habitability without needing to generate a field of its own. Number 8. Atmospheric density on supersized moons creates stable surface conditions that were previously assumed to require planet-scale mass. There is a threshold assumption embedded in most habitability models that a body needs to be roughly Mars-sized at minimum to retain a meaningful atmosphere over geological time. Below that mass, The gravitational pull is insufficient to prevent atmospheric escape, particularly for lighter molecules like water vapor and molecular nitrogen. Moons in our solar system largely fall below that threshold, which is why none of them have dense, stable atmospheres beyond Titan. But Titan itself is the key exception that reveals the flaw in the assumption. Titan is smaller than Mars and has no magnetic field to speak of, yet it possesses an atmosphere denser than Earth's. The primary reasons are its distance from the Sun, which reduces thermal escape velocity for atmospheric molecules, and the cold temperatures that keep even nitrogen in a relatively low energy state. Exomoons orbiting gas giants at moderate distances from cooler stars would replicate these conditions naturally. If the Moon has sufficient mass, and mass scales are broader than originally expected given updated formation models for gas giant satellite systems, it can gravitationally retain a thick atmosphere of nitrogen, carbon dioxide, or even oxygen depending on its surface chemistry. Observational candidates identified through transit timing variations around several Kepler and TESS targets suggest the presence of moons with estimated masses between 0.5 and 2 Earth masses. At that scale, atmospheric retention is not speculative. It is expected. A moon of that mass, shielded by its planet's magnetosphere, with tidal heating providing internal energy and a thick atmosphere providing surface pressure and thermal regulation, is not a marginal candidate for habitability. It is a strong one. Number 7. The subsurface ocean paradigm means habitable environments do not require surface conditions to be hospitable at all. This is possibly the most significant conceptual shift in astrobiology in the last 20 years, and it originated entirely from studying moons in our own solar system. Europa, Enceladus, and potentially Ganymede and Callisto all appear to harbor liquid water beneath insulating ice shells. Enceladus actively vents water vapor and organic molecules into space from fractures in its south polar region. The chemistry detected in those plumes includes molecular hydrogen, which on Earth is a chemical energy source for microbial life in deep-sea hydrothermal systems. The relevance to exomoons is direct. If a moon does not need to have a habitable surface to contain a habitable environment, then the number of qualifying moons expands enormously. Surface temperature becomes less relevant. Atmospheric composition becomes less relevant. What matters is whether the interior contains liquid water in contact with a rocky core, where chemical energy sources can sustain metabolism. Tidal heating, as discussed, provides the energy. Rocky cores provide the mineral substrate. Water provides the medium. The ice shell provides insulation and radiation protection simultaneously. This model does not depend on being in any particular habitable zone. It does not depend on atmospheric retention. It does not even depend on the host star being stable. A moon around a gas giant orbiting a red dwarf that produces constant flare activity could still maintain a perfectly viable subsurface biosphere because the relevant environment is kilometers beneath the surface, completely decoupled from external stellar conditions. The number of moons in the galaxy that could satisfy these interior conditions is conservatively estimated in the tens of billions. Number 6. Orbital resonance chains create long-term stability that prevents the tidal heating mechanism from either burning out us or tearing the moon apart. Tidal heating is not inherently stable. If a moon's orbit circularizes over time, which gravitational interactions tend to cause, the tidal flexing decreases and eventually the heating stops. If the orbit becomes too eccentric, the heating becomes extreme and the moon's interior can partially melt, leading to catastrophic volcanic resurfacing that destroys any existing biosphere. The mechanism that prevents both failure modes is orbital resonance, where multiple moons in the same system lock into integer orbital ratios that continuously pump eccentricity back into each other's orbits. Jupiter's inner moons demonstrate this precisely. Io, Europa, and Ganymede maintain a 1 to 2 to 4 resonance that has persisted for billions of years. This resonance is what keeps Europa's orbit slightly eccentric, which is what maintains the tidal heating, which is what sustains the subsurface ocean. Without Ganymede's gravitational influence, Europa's orbit would have circularized long ago and the ocean would have frozen solid. The implication for exomoon systems is that habitability is not just about individual moons. It is about the architecture of the entire satellite system. Gas giants that form with multiple large moons in resonant configurations create self-sustaining heating mechanisms that can operate for the full lifetime of the host star. Formation models indicate that resonance chains are not rare outcomes. They are a natural product of moon formation in circumplanetary disks, where migrating protomoons frequently capture into resonance during the dissipation phase. Every gas giant that formed a family of large moons through this process is a candidate for containing at least one member with sustained tidal heating in a stable orbital configuration. Number 5. The statistical abundance of gas giants in the galaxy means the number of potential host systems is staggering. Current exoplanet surveys have confirmed over 5,000 exoplanets, and the data consistently shows that gas giants are common. Approximately 10 to 15% of Sun-like stars host at least one gas giant. For M-type dwarf stars, which constitute roughly 70% of all stars in the Milky Way, the occurrence rate is lower but still significant. Even conservative estimates place the total number of gas giants in the galaxy somewhere between 10 billion and 50 billion. Each of those gas giants, based on formation models calibrated against our own solar system, is expected to host a system of moons. Jupiter has 95 confirmed moons. Saturn has over 140. The large regular moons, the ones formed in circumplanetary disks and most likely to be massive enough for habitability considerations, typically number between 2 and 7 per gas giant. If even 1% of all gas giants in the galaxy host a moon with conditions compatible with subsurface or surface habitability, the resulting number of habitable moons exceeds the number of habitable planets by a wide margin. This is not a speculative projection. It is a straightforward multiplication of observed occurrence rates and formation model outputs. The reason this matters is that it reframes the entire search. If habitable moons outnumber habitable planets by 5 to 1 or even 10 to 1, then the probability of life existing somewhere in the galaxy is not modestly affected. It is categorically different from what was assumed under a planet-only model. Number 4, moons orbiting gas giants in the habitable zone get both energy sources simultaneously, and that combination produces the most Earth-like conditions possible outside of actual Earth-like planets. The scenarios described so far have focused on moons that rely on tidal heating as their primary or sole energy source, but gas giants also exist within the habitable zones of their host stars. Kepler data has confirmed dozens of Jupiter-sized and Saturn-sized planets orbiting within the liquid water zone of their stars. A large moon around one of these planets receives stellar radiation at the right intensity for surface liquid water and receives tidal heating as a supplementary internal energy source. This dual energy configuration produces a world with active geology, a warm interior, volcanic recycling of atmospheric gases, and surface temperatures regulated by both solar input and atmospheric greenhouse effects. The geological activity driven by tidal forces ensures continuous outgassing, which replenishes the atmosphere over time and maintains a carbon cycle analogous to Earth's. The stellar energy provides the surface warmth. The combination generates conditions that are not merely habitable in a minimal, subsurface-only sense. They are potentially habitable in the full surface biosphere sense, with weather, liquid surface water, and photosynthetic potential. You are looking at a category of world that functionally replicates the Earth model while existing as a satellite rather than an independent planet. The candidates already identified through transit timing anomalies in Kepler and TESS data are being prioritized for follow-up observation with the James Webb Space Telescope precisely because their atmospheric signatures, if detectable, would be the most interpretable evidence of biological activity outside our solar system. Number 3, Chemical energy independence from starlight means life on exomoons could exist in complete darkness and still sustain complex ecosystems. Earth's biosphere is overwhelmingly solar-powered. Photosynthesis drives the base of almost every food chain on the planet's surface. This created an implicit assumption in astrobiology that life requires starlight, either directly or indirectly. The discovery of chemosynthetic ecosystems at deep-sea hydrothermal vents on Earth dismantled that assumption entirely. Entire communities of organisms, including tubeworms, shrimp, crabs, and microbial mats, thrive at the bottom of the ocean in total darkness. Their energy source is chemical, derived from the reaction between hydrogen sulfide, or molecular hydrogen, vented from the Earth's interior, and dissolved chemicals in the surrounding water. The relevance to exomoons is that tidal heating produces exactly the conditions needed for hydrothermal activity on a rocky seafloor beneath an ice shell. Hot rock interacting with ocean water generates chemical gradients. Those gradients represent exploitable energy for any biochemistry capable of catalyzing the relevant reactions. This means an exomoon does not need to be anywhere near a star to support life. It needs a rocky interior, liquid water, and sustained heat. Tidal heating provides the heat. Resonance chains sustain the tidal heating. The gas giant's gravity provides the structural framework for the entire system. Life that originates in these conditions would have no dependence on or even awareness of the host star. Its entire existence would be defined by the geochemistry of its ocean floor and the gravitational mechanics of its orbital system. If this type of life is possible, and the biochemical principles observed at Earth's hydrothermal vents strongly suggest it is, then every icy moon with a subsurface ocean and tidal heating becomes a live candidate. The scope of that candidate pool, as established by the numbers discussed earlier, is enormous. Number 2, next-generation detection methods are approaching the sensitivity needed to confirm exomoon atmospheres directly, and the first confirmed detection will restructure observational priorities across every major space agency. Exomoons have been theoretically predicted for decades, but direct detection has remained just beyond instrumental capability. The primary detection method currently in use is transit timing variation, where the gravitational influence of a moon causes measurable shifts in the timing of its host planet's transit across the star. A secondary method is transit duration variation, where the planet's transit lasts slightly longer or shorter depending on the moon's position. Both methods have produced candidate signals in Kepler data, most notably around Kepler 1625b, where a Neptune-sized moon candidate was identified, and Kepler 1708b, where a second candidate was later reported. These detections remain debated, but the statistical methods and instrumental precision are improving with each data release. The James Webb Space Telescope represents a generational leap in capability for this specific problem. Its infrared sensitivity allows it to detect atmospheric absorption features in transiting bodies at sizes and temperatures relevant to large exomoons. If a moon transits its host star independently or simultaneously with its planet, and that moon has a thick atmosphere containing water vapor, carbon dioxide, methane, or oxygen, JWST can in principle identify those spectral features. The detection of methane and oxygen together in an exomoon atmosphere would constitute a biosignature, a chemical combination that is thermodynamically unstable without a continuous biological source. This is not a distant future scenario. Target lists for JWST exomoon atmospheric characterization are already being developed using refined Kepler and TSS candidate data. The European Space Agency's Plato mission, scheduled for the late 2020s, will further expand the candidate pool with higher precision transit photometry optimized for longer period planets where large moons are most expected. The detection pipeline is operational. The instruments are either deployed or in final development. The first definitive exomoon atmospheric characterization is a question of when, not whether. Number 1, if even a single exomoon is confirmed to harbor conditions compatible with life, the mathematical implications propagate across the entire galactic model, and the answer to whether life is common becomes effectively settled. This is where every preceding point converges. The galaxy contains somewhere between 100 and 400 billion stars. A significant fraction of those stars host gas giants. Each gas giant hosts a system of moons. Formation models predict that large, geologically active moons in resonant orbital configurations are a standard outcome of giant planet formation. Tidal heating provides energy independent of stellar distance. Magnetic shielding provides atmospheric protection independent of the moon's own field strength. Subsurface oceans provide habitable environments independent of surface conditions. Chemical energy sources provide metabolic fuel independent of starlight. Every one of these factors operates through well-understood physical mechanisms observed in our own solar system. None of them require exotic conditions. None of them require fine-tuning beyond what standard planetary formation produces routinely. If one confirmed detection demonstrates that these conditions align to produce a viable biosphere on a moon orbiting a gas giant in another star system, the inescapable conclusion is that the galaxy contains billions of such environments, not thousands, not millions, billions. The reason this conclusion follows is that the conditions are not extraordinary. They are the default output of ordinary gas giant formation around ordinary stars with ordinary moon systems maintained by ordinary gravitational dynamics. You are living at the specific moment in history where the instruments capable of making that determination exist, and the observations are underway. The framework has already shifted among the researchers directly involved. The public understanding has not caught up. The habitable zone, as traditionally defined, that narrow band around a star where a rocky planet might hold liquid water on its surface, represents a small fraction of the actual habitable real estate in any given system. The moon's orbiting gas giants, heated from within, shielded from without, sustained by resonance chains that operate for billions of years, collectively represent the larger share. Life, if it exists beyond Earth, is more likely to be found on a moon than on a planet. That is not a speculative claim. It is the conclusion that follows directly from the physical constraints, the observed formation rates, and the detection capabilities now being deployed. The question is no longer whether habitable environments exist beyond Earth. The data already indicates they do, in numbers that make isolation functionally impossible. The only remaining question is confirmation, and the process of obtaining it is already underway.